So let's do a problem in that this is sort of one of those things that make you say, huh, well, that's not what I thought. Okay, so here's this function, x squared sine 1 over x. And we're going to compute the derivative of this function. In fact, it really says to do three things. So the x squared sine 1 over x, the problem is that it's really not well defined when you plug in 0 into sine 1 over x. But when you multiply it by x squared, you're fine. If you think about what's happening, you can sort of get an idea of what this graph would do. Just graph your x squared function and your negative x squared function. And what's going to happen is that the sine 1 over x has to go in between. So it's oscillating a lot, but as you come in, it doesn't oscillate too much. In other words, it's collapsing down. So we're going to follow these 3 bullet points. So how do you take the derivative of x squared times sine of 1 over x?
You have to use product and chain rule.
Product rule and chain rule, which is why we had to wait till now. See, before now we couldn't do this, but now we can. All right, so product rule, the derivative of the first is 2x times the second sine 1 over x plus x squared, which is the first function, times the derivative of sine 1 over x. The derivative of sine? Cosine. What do you plug into cosine? 1 over x. You leave the inside alone. And then the derivative of the inside. And 1 over x is x to the negative 1. So the derivative of that is negative 1 over x squared. And so if you clean it up just a little bit, not hard to do, you get 2x sine 1 over x. And here you see that the x squareds cancel. So you get a minus cosine of 1 over x. Okay, so that was the first point. Our second point. What's the limit as x goes to 0 of f prime of x? So here, this is our f prime of x. So what's the limit as x goes to 0 of 2x sine 1 over x minus cosine of 1 over x? Now, the first part is something we've actually done before. And we did this, we talked about squeezing. Because what's happening is that sine 1 over x is going up and down, but then you're multiplying it by x, which is getting small. So if you have something that's going to 0, multiplied by something which is bounded, the whole thing has to go to 0. That's what the squeeze theorem would tell us. So the first part says, hey, this is no problem. This is going towards 0. What happens to cosine 1 over x as you get closer to 0? Well, it looks like this. It's that same phenomenon that you see with sine of 1 over x. Because what's happening is the cosine is trying to do oscillations. So if you just do cosine, and you think about what the cosine curve normally does as you go to infinity, it oscillates up and down. But now what's happening is that you have to press all those infinitely many oscillations into a very small window. And so it tries to go crazy. So what's going to happen to our limit? This part's going to 0. This part's oscillating up and down between 1 and negative 1. The net result is that this limit does not exist. So that says that our derivative at 0 is what? Well, it doesn't say anything. It just says that the limit of the derivative as we go to 0 doesn't exist. Suppose we wanted to find f prime of 0. How can we do it? Well, can we find f prime of 0 by plugging it into here? Into this expression? No, you can't do it. It's not possible. Because cosine of 1 over 0 is undefined. So how can we do f prime of 0? Well, the answer is we go back to the definition. And we're going to find the definition of the derivative. So if I wanted to find f prime of 0, One way I can do is I could say, well, this is the limit as h goes to 0 of f of 0 plus h minus f of 0 all over h. And it's good to know the definition of the derivative. As we've been mentioning, it's one of those questions that has a very high likelihood of being on an exam. So, let's see what that does. So that becomes the limit as h goes to 0. F of 0, what is that? It's 0. Because it says here, if I plug in 0, I'll put 0. Now, f of h, well, I'm not 0, so I'm going to be h squared sine 1 over h. And I'm going to divide it downstairs by h. So this becomes the limit as h goes to 0. I can cancel off a single h, so I get h times sine of 1 over h. Well, what does this limit do? We can squeeze it. It's essentially what we're doing here. What you can do is you can bound sine 1 over h between 1 and negative 1. So h sine 1 over h, you can essentially bound between h and negative h. And those go to 0. Which means f prime of 0 is 0. So this is a function which has this following interesting fact. We can take the derivative literally everywhere. Because we've checked. We have the 2x sine 1 over x minus cosine 1 over x if x is not 0. And then it's 0 if x equals 0. But f prime of x is not continuous. So that's kind of strange. Because oftentimes we think of like, oh, if I start with a nice function and it has a derivative everywhere, the derivative has to be nice. It has to be continuous. And the answer is no, it doesn't. Because math is weird. There's all sorts of crazy functions out there. And this isn't even that crazy by the grand scheme of math. So you always should be a little bit careful. This is why mathematicians have numerous breakdowns. They worry about all these details. There's a lot of details. But all right. Okay, good. So what's today's topic? Well, we're going to continue with our chain rule. And we're going to talk about sort of a different notation. So this is called Leibniz style. So Leibniz, if you had gone to school in Germany and we talked about calculus, we wouldn't mention Newton very much. We'd just say, yeah, there was this other person named Newton who did calculus. But Leibniz, he was the German. He did calculus as well at the same time. So how does it work? So he's the one who uses that d notation, like dy dx. What we want to think of is we have this sort of sequence of chains of variables. So here I'm having as y is f of g of h of x. But now what we're going to do is we're going to sort of like pull it apart and say, well, look, y is a function of something. I'll call that a function of u. And then u is itself a function of something. I'll call that, say, g is a function of v. And v is something. It's h as a function of x. So if you were to actually sort of plug in, so replace v by h of x, replace u by g of h of x, you get to the same thing that you had. But what you're doing is you're sort of pulling apart so that at every level you have something much simpler. You don't have this sort of layer upon layer upon layer of complexity. You just sort of have multiple layers going on, all separated out into their different strata. So you can think of this in a nice way as a vertical chain where you can see how do the different variables relate. And this sets us up for one thing we'll talk about in a year from now, multivariable calculus. How do the variables relate to one another? Well, you can say, look, y is a function of u, which means that really y depends on u. As I change u, I change y. And u is a function of v. As I'm changing v, I'm changing u. And v is a function of x. So now, what does the chain rule become? Well, the chain rule says, if I want to find dy dx, what I look at is the following thing. I say dy dx, it depends on how does y change with u, so that's the dy du. How does u change with v? That's the du dv. And how does v change with x? That's the dv dx. So that's what we get. Now, there is this tendency to see this formula and say, it makes sense. Because what's happening? Well, the du's are canceling and the dv's are canceling. All that doesn't cancel is the dy on the top and the dx on the bottom. And so you say, I believe this, easy proof. But here's the word of warning. You shouldn't think of it as dy over du as being two separate things. That's just a notation for one object. So dy over du, this is by itself a single thing. Du dv is a single thing. So it's not like, there's this du piece here and a du part there that cancels. There's a little bit more subtlety to that. But in the end, if it helps you, convinces you that it's true, it's not the worst thing to think about. So let's use the Leibniz chain rule notation to actually do this. Y equals cosine of x squared to find dy dx. Now, how do we do this? Well, we'd like to break this up into a series of functions. So in fact, let's see if we can do it similarly to what we have here. We have three functions. So if I were thinking this as a series of functions, what's the outermost function? Yeah, so we're going to say our outermost function we'll say is e, and I'm going to call it u. So then u, that's the inside part. That's the cosine of x squared. So again, I'm going to think of this as, what's the outermost function of cosine of x squared? The cosine is. So I'm going to let u become cosine of v. Then I say, well, what is v? Well, that's x squared. Okay, now we've sort of gone down to more or less as far as we can go. You could say, well, it's w squared. And then I say, well, what's w? W is x. Okay, well, all right, fine. Okay, so we have y is e to the x, u is cosine of v, v is x squared. So, if we want to find dy dx, then what we have is we have the following. We say this is dy du times du dv times dv dx. And what is the derivative of y with respect to u? E to the u. The derivative of u with respect to v? Negative sine of v. And then the derivative of v with respect to x? 2x. Now normally, if we want our answer, we would then say, okay, if we substitute back, well, this would become e to the u, which is cosine of v, but that becomes cosine x squared. And then there's a negative sine of v, which is x squared. And then there's a 2x. So you'll see this is the same thing that we had before. It's just sort of saying, let's pull things apart. Now, at this point, you're probably thinking, if it's the same thing that we had before, is there really any advantage to doing it this way? It depends what you're going after. There are some cases where it is advantageous to sort of break things apart. And I will say that usually the greatest advantage you'll have is when there's an evaluation. If there's not an evaluation and you have to put things back as they were, it's more or less the same amount of work as it was before. And you'll get the same answer. And that's about all I have to say with that. You're not going to see this too much, so don't stress too much about trying to figure out exactly how it works. The more you practice with it, when it does come up, it's fairly intuitive. So we're going to do a bunch of examples, because examples are good. And these are chain rule examples. So, suppose the line y equals 5 minus 3x is tangent to y equals f of g of x at x equals 1. F of x is invertible, okay, all right, whatever that means. And we have the following information about f of x. Find the tangent line to y equals g of x at x equals 1. Now, if I'm looking for the tangent line to y equals g of x at x equals 1, what information do I need? So I'm looking for a tangent line to a curve at a particular point. What do I need to find? I need to find a point and a slope. So that translates into saying I need to figure out what is g of 1 and what is g prime of 1. That's what I'm after. So I don't have that information yet, but by the time we finish it, I'm optimistic we will. We are told that there's this line y equals 5 minus 3x, and it's tangent to y equals f of g of x at x equals 1. So let's call this h of x. That's our f of g of x, just for convenience in terms of notation. Because we have the tangent line at 1, that gives us useful tools. So tangent line at 1 tells us that we know what h of 1 is and what h prime of 1 is. So this is, again, a philosophy that you should always think of a tangent line as having our two pieces of information, the value of the function at that point, the value of the derivative at that point. And you should be comfortable going back and forth. So we have the tangent line at 1. What is h of 1? H of 1, so we plug 1 into the tangent line. So h of 1 is 2. What is h prime of 1? Negative 3. It's the slope of our tangent line. So we know that h of 1 is 2 and h prime of 1 is negative 3. Now, what else do we have? Well, we know that h of 1 is f of g of 1. But we just figured out that h of 1 equals 2. So f of g of 1 equals 2. So that means I need to scan and say, when does the output of f give 2? So we scan along the row, and we say, negative 3, no, 0, no, 1, 2. 2, there's the 2 right there. What output was it? What input do I have? 3. That says, in order for f of something to be 2, my something, this inside, had better be 3. So we now know what g of 1 is. G of 1 is 3. But that's not enough. We need we need g prime of 1, so we need to use the fact that about h prime of 1. So what is h prime of x? F prime of g of x times g prime of x. Now, we know h prime of 1 is equal to f prime of g of 1 times g prime of 1. And the reason we know that is we just took everywhere we saw an x and we put a 1. That's not too surprising. But we also know some things. H prime of 1 is negative 3. That's equal to f prime of g of 1. Well, we just figured out what g of 1 is. That's 3 times g prime at 1. What is f prime at 3? It's 2. We can come down and read it off. So, what is g prime of 1? Negative 3 over 2. So now, good news, we have our point, g of 1, and we have our slope, g prime of 1. So we can put those two things together. So y minus our y value, 3, is equal to our slope, negative 3 halves, times x minus our x value, which is 1. And that's it. We're done. All right. I actually like this one. It's a little bit different. It's a little bit different. This one is probably not a surprise. Just a nice fact to know. There's a lot of special cases about the chain rule. So sometimes the chain rule gets used so often, you say, well, what if we have a function inside the exponential function? What if we have a function inside a trig function? One that gets used a lot, that you should just sort of make it instinctual, is what if you have a function inside a power? Something raised to the kth power. What's the derivative? Well, if you see a function raised to the kth power, you should really think of it as my inside function is f of x, my outside is like x to the k. And the derivative of x to the k, well, you bring the k down, then it'd be whatever was in the inside to the power k minus 1. Well, the inside was f of x. So k, f of x to the power k minus 1 times the derivative of the inside, f prime of x. This is just a really nice rule to remember. It gets used a lot, and so it's good to learn it, good to know it. The more you know. So we can try an example. So this one goes to a lot of extremes, lots of powers. So suppose we want to find this derivative. All right, well, a little bit of pause here. Sine, the trig functions in general, because they're so old, they predate good notation. And so as a consequence, they have bad notation. So when you see sine 20 here, what does that mean? Well, what it means is it's really sine of whatever I was happening to plug into there. So 1 plus x squared to the 10th is what I'm plugging into sine. And I'm raising that to the 20th. So just keep that in mind. So whenever you see sine to a number, we'd like to think that as meaning what I'm raising my function to that number. I will tell you that there's one exception, which is when you have the negative 1, which is just a sad thing. Because tangent to the negative 1 of x, a lot of people misread that as 1 over tangent of x, but almost always it's really supposed to be arctangent of x. And one of these functions is so much nicer. That's the exception. All right, so here we go. Now, are we going to get a chance to use this new rule, or rather I should say this adaptation of the rule? And the answer is, oh yeah, because we've got powers and powers and powers. Towers of powers, if you will. So we work our way from the outside in. All right, so what's the very first thing I'm going to write down? Well, the very first thing I'll write down, because this is something to the power of negative 50, so I have something to the negative 50, so the first thing I write down is that exponent, negative 50. And then everything on the inside. Oh boy, this is going to be one of those problems where we have to go to the second line, isn't it? Yes, it is. Yes, it is. And it's also one of those problems where you have to pay attention to. There we go. 20 to the negative 49. All right. Are we? Yeah, negative 51. Good. I'm glad you're paying attention. Aha, it was a test. And you all passed. I hope you do that well on the real test. All right. Subtract 1. Now, are we done? No. Times the derivative of the inside. Okay. Well, the derivative of 1, that's 0. So now we come to the sine to the 20th power. What happens here? 20 comes down, and then it's sine of 1 plus x squared to the 10th to, I better let you do this one, to what power? 19. Okay, good. Now are we done? No, and I can see I should not have put my parenthesis there. Okay. What comes next? Well, the next layer is the sine. What's the derivative of sine? Cosine. All right, at least that one, I got that one right. All right, now are we done? No, because we said I'll have to keep going. 1 plus x squared to the 10th. What's the derivative of 1 plus x squared to the 10th? 10 comes down. 1 plus x squared to the 9th. And Still not done. What's left? 2x. All right. So there we go. There it is. It's that times that times that times that times 2x. Yep. Chain rule. Okay, good times. A particle moves so at time t greater than 0, its position is given by the following function. S of t is t times e to the negative t squared over 8. Determine when the velocity is 0. Determine when the acceleration is 0. So we have our position, S of t, that's t e to the minus t squared over 8. We want to talk about when is the velocity 0. So how do I go from position to velocity? Take the derivative. So the velocity is the derivative of position. How do I take this derivative? Well, what is the derivative here? Well, product rule. Derivative of t would be 1 times the second function we leave alone, e to the minus t squared over 8, plus t times the derivative of e to the minus t squared over 8. Well, chain rule. E to the what power? Negative t squared over 8 times the derivative of the exponent, which is negative 2t over 8. So I can think of that derivative of t squared as being 2t, and then I still have that negative 1 over 8. Now, of course, we can clean this up a little bit. We could, for instance, say, hey, both these terms have e to the negative t squared over 8. So if I were to factor that out, I would have 1. Then I have a minus from there. There's t squared because there's 2 t's. And then there's an over 4. 2 over 8 makes over 4. So there's our derivative. Now, one of our questions was, when is the velocity 0? So let's figure that out. When does 1 minus t squared over 4 times e to the minus t squared over 8 equal 0? So our 0 could come from one of two places, because there's two things multiplying. When does e to the minus t squared over 8 equal 0? When t is... Yes, that's the correct answer. There's nothing. Good. All right. You're on the ball. Okay. How about this? When does 1 minus t squared over 4 equal 0? So you could solve that. That becomes t squared equals 4. Or normally it would be t equals plus minus 2, but you double check. In our case, we want t to be positive. So we don't have to worry about the plus minus in this case. You should always double check, though, because sometimes you do need to worry about time being negative, sometimes you don't. In this case, we're okay. So t equals 2. This is when our velocity equals 0. All right. Now, we're only halfway done, because we also get to talk about acceleration. So now we're going to take the derivative again. And it doesn't matter which form we use. I'll start with this. Well, I guess I'll do our simplified form. So the derivative of velocity gives acceleration. So what's the derivative of 1 minus t squared over 4? Negative 1/2 t. The derivative of 1 is 0. It's a constant. The derivative of t squared would be a 2t. So we have a minus 2/4, which is a minus 1/2 times t. Then it's e to the minus t squared over 8. Then we're going to add, leave the first alone, 1 minus t squared over 4. And then times by the second. That's e to the minus t squared over 8. And then what? Well, times the derivative of times the derivative of minus t squared over 8, using the chain rule, which is the same thing as what we had up here. And I'll simplify it this time. It's minus t over 4. All right. Well, let's pull out some common things. What are some things that both terms have? They both have e to the negative t squared over 8. So that's a common thing, and I can pull that out. Is there anything else that's common? They actually both have a t. So I could pull that out. So once we pull that out, we get t e to the minus t squared over 8. And what's left? Well, from the first term, we have minus a half left. From the second term, we're going to have 1 minus t squared over 4 times minus a fourth. All right, we're going to get lots of fractions here. That's okay. Fractions don't intimidate us too much. We can always remove them later. So again, we're pulling out what they have in common and then playing with what they have left. So that's t e to the minus t squared over 8. Let's see, we have minus a half minus a fourth, because the 1 will multiply by this negative fourth from the backside. So that's minus 3/4. Then here, minus minus makes plus t squared over 16. And 4 times 4. Now, we could even go one step further and say, if we really wanted to get rid of fractions, what could we pull out? Well, what's the common denominator? What would we need downstairs? A 16th. So if you were to pull out a 1/16 and clean it up, what you'd have left is you'd have t squared. Oops, I'm almost off. There we go. You'd have t squared, and then what would the minus 3/4 become? Minus something. Okay, we've narrowed it down to something. Minus 12. Now, if you're wondering how do you get to that point, just think about if I pull out 1/16, it's the same as multiplying each entry by 16. So, for example, 16 times t squared over 16, the 16's cancel. 16 times 3/4, well, you get 4 goes into 16 with 4 left over. So it becomes 3 times 4, which is 12. So, similar question we can ask. If we want the acceleration to be 0, well, t could be 0. No, t has to be positive. E to the minus t squared over 8, well, that can never be 0. I should have pointed to the 1/16. Can 1/16 be 0? No, it's too busy being 1/16. It doesn't have time to be 0. So that means if we're going to be 0, t squared minus 12 has to be 0. Well, how can I figure out when does t squared minus 12 equal 0? That would be the same as when t squared equals 12. Take the square root, and what do we end up with? You end up with square root of 12. Now, you could write that as 2 square root of 3, but you don't have to. And so, square root of 12, which, again, you could write as 2 square root of 3, this is the time when your acceleration is 0. All right. Suppose that the depth of a pond in inches is modeled by the following. So d for depth. D as a function of time is 45 plus 3 cosine pi 6t, where t is measured in months. So in particular, the pond might get more shallow as the summer comes to an end, but of course it's going to get deeper in the spring when the rain comes, and all sorts of things cause this to go up and down. So here we have, all right, what is the rate at which the water level is changing at time t equals 4 months, including units? So, what's the key word here? Rate is a key word. When you see the word rate, what should you think of? You should think derivative, because derivatives are about rates. How is something changing? So, when we see that, we say, okay, we have our function. Our depth at time t is 45 plus 3 cosine of pi 6 times t. So if I want to know a rate at 4 months, it's really asking me for what is d prime of 4. So if I want d prime of 4, the first step is what's d prime at t in general? What's the derivative? Well, the derivative of 45? 0. So we have what? Well, we have the 3. That's going to come along. That's constant multiple rule. Derivative of cosine? Negative sine. So I'm going to put a parenthesis here to remember that we're multiplying. Negative sine. Inside we put pi over 6t by the chain rule. All right. Anything else? Times pi over 6. And that comes from the chain rule. The root of the inside, pi over 6t. Now we can clean this up a little bit. For example, 3 goes into 6. So that would be pi over 2. And I'll put negative in front. Negative pi over 2 sine of pi over 6t. Now we plug in 4. So we see, okay, so that's negative pi over 2 sine of pi over 6 times 4. Or if you like, that's negative pi over 2 sine of 2/3 pi. Well, do we know what the sine of 2/3 pi is? If you think about a circle, and the reason we say think about a circle is trig comes from circles. Sine, does that correspond to x or y values? Well, the reason I'm asking the question, you meant y, the variable. Okay, all right. All right, I make that mistake so many times. All right. Now, 2/3 pi, if you actually look at the angle, it's over here. So it's like you went a full pi, but then you went back a third. Or if you like, you went 2/6 of the way around. So we're interested in the y values here. It turns out that sine of 2/3 pi is the same as sine of 1/3 pi, and you're probably thinking, I don't know that one either. And at this point I'll say, sine of 1/3 pi, if you really needed it, we'd probably throw that on the test. In that we've thrown it on the test every time for the last several years. We do expect you to know things like 0 and pi halves and pi fourths. But sometimes pi 6, pi thirds, that's not maybe so obvious. Does anybody know what it is, though? Square root of 3 over 2. So this becomes negative pi halves times square root of 3 over 2, which is minus square root of 3 pi over 4. Now, it's said to include units. Now, if you see something that says include units, if you want full points, you should include the units. It's an old trick that you learned. It happens a lot. So how do we figure out our units? Well, you look at d. What is d? Depth in inches. So that says the units of the function is inches. Now, that's the output. So whatever the units of the output is for d, that goes in the top. So that's inches per. Now, to figure out what's downstairs, you say, what are the units of the input? So it's time. Time is measured in months. So inches per month. So that's the rate at which the water level is changing, minus root 3 times pi over 4. There's a second question. Should we expect that rate to increase or decrease? In other words, what's happening to the rate of the rate? What do I look like? What do I want to be looking at if I want to understand the rate at which the rate is changing? The second derivative. Because if I want to know how the rate is changing, whenever I want to know how something's changing, I look at a derivative. So it's a derivative of a derivative is the second derivative. So d double prime. Well, taking the derivative, that would be negative pi halves. Derivative of sine? Cosine. Pi 6 times t. So we plug in 4. So we end up with negative pi halves times cosine. Multiply by pi 6. Yep, sorry. cosine of, and it's still going to be 2/3 pi times pi 6. Now the good news is, if I'm talking about increasing or decreasing, I really don't need to know the number. What do I need to know? Positive or negative. Increase, that's when our derivative is positive. Decrease is when our derivative is negative. That's our intuition. We're going to go more into that later on in the course. But for right now, that's good enough. So what do I need to figure out? Well, pi over 2 and pi over 6, I really don't need to know those two, but I should probably know cosine of 2/3 pi. So that's the x value. So the x value is the cosine. So what can I say about cosine 2/3 pi? Is it positive or negative? It's negative. And I have another negative up front. So their negatives combined tell us that our second derivative at 4 months is positive. So the water level is dropping. That we know, because the first derivative is negative. But the rate at which it's dropping is going positive. Now, how do we interpret that? Well, if I have a negative number, I'm going down, but the positive says I should be moving in an upward direction. So, we have to think about this. Should we expect the rate to increase or decrease? This is one of those wonderful ambiguities. What's the answer? I would say that if you were talking to someone at home, your rate should be decreasing. You can make an argument both ways. But here's the thing. Our rate is negative, but it's going in a positive. The second derivative is positive, which means I'm pulling it up. So I'm going to be pulling it up closer to 0. So the rate is actually going to be decreasing, relatively speaking. Okay. Of course, it all depends on sign. This is, I should say this is an ambiguous answer. You could justify both of them. There's an interesting newspaper clipping from the 1970s about how someone said, well, the interest rate is dropping, but not as much as it used to be dropping. And they said that's the only time anybody ever tried to use the third derivative in politics. So, all right. I should avoid trying to justify that answer. So here we go. One last question for today. Using the graph of y equals f of x shown below, find the following. So this is, can you read information from the graph? But the thing is, we only need the graph to tell us things that we need to get out of it. So let's figure out what we need from the graph before we try to understand it too much. So this says, take the derivative of f of x squared, and then plug in x equals 2. Now, the derivative of f of x squared is equal to, can anybody tell me? F prime of x squared times 2x. So if I want to take the derivative of f of x squared, and I see this line x equals 2, remember that just means plug in 2. So this would be f prime at 2 squared, which is 4, times 2, which is 4. So we come over to our picture, and we say, all right, here's 4. So I'm trying to understand what the derivative at 4 is. Now let's be careful here. I want the derivative at 4, not the function at 4. The function at 4 turns out to be 4. The derivative at 4 turns out to be 2, because the function at 4 is a straight line. And if I want to understand the change, I say, well, what's the tangent line? Well, the tangent line is just that straight line segment that I see. And the slope of that line is 2. So 2 times 4, which is 8. For the other one, well, the derivative of f of x, well, that's f prime of f of x times f prime of x. So we evaluate it too. And when we do this, this is going to get us into one of those, just sort of follow your nose. Work through one layer at a time. When you're taking derivatives, you work... Oh, is that one? Oh, more interesting. Okay. When you're taking the derivatives, we oftentimes say, look, do it one layer at a time. Work from the outside in. When you're evaluating, work from the inside out. what can we say about f of 1? F of 1 is equal to 4. So this is f prime of 4 times f prime of 1. Now we actually found f prime of 4. Do we remember it? 2. Good. We have good memory. F prime of 1, well, what is f prime of 1? Negative 1. And therefore our answer is negative 2. And that's all we need. All right, now we're ready. We know everything. Good luck.